Welcome back to Astronomy. This is Chapter 6 on telescopes, portals of discovery. As you look at this picture, can you discern where in the sky it's looking? This is actually a picture from a camera whose shutter was left open for many hours, and so you're watching the star trails go around as the stars go around the sky. They come up in the east, they go down in the west, and you're looking at the trails left on the image from the camera. But it's pointing right at the North Star. The North Star would be right about here, and all the stars actually move around the North Star through the course of the night as the Earth rotates. You might think it weird as you look at this picture. The main part of this picture is not the light trails from the stars, but rather those satellite dishes down below. You might think it weird that on a chapter on telescopes, that this is my opening picture. But as you'll see, while these don't look like what most people have in mind when they visualize a telescope, these are actually telescopes that look not at visible light, but at radio waves. And so we will talk about all kinds of telescopes as we go through this video. As we think about the design of a telescope, at least the original design, let me give you some basic anatomy. A lot of it is based on optics that occur in our eye. So here is a very basic picture of the eye, and light comes in and there's a lens as the light enters through the pupil, the opening. This is the black circle in your eye. It's actually a transparent opening. It just looks black because no light is coming off of it. Light goes through the lens. It goes through the inside of the eye and it makes an image on the retina. Actually, the light activates molecules in the cells in the retina. And what happens to the electrical activation of those molecules, it goes through the optic nerve to the brain, and these light signals get translated as images. Similar to the eye, this is how the first telescope designs worked. Light rays come in. We can think of them as parallel light rays. They get bent or refracted by the lens, and then they are focused as they converge, the light rays converge, they focus on the retina. And this is generally what happens with any convex lens. Like you see here, parallel light rays come in and they converge to a focal point, or the focus. And this is what's called refraction. Refraction just means bending, the bending of light. So refraction can cause parallel light rays to converge to a focus. There are two basic designs of telescopes. I just showed you refraction from a lens. The first type of telescope, the original type, used by Galileo in the early 1600s, is called a refracting telescope, otherwise known as a refractor. It focuses light using a lens. The other type, which is more often used with professional grade telescopes, is a reflecting telescope, otherwise known as a reflector. It focuses light with a mirror instead of a lens. This picture is of the largest refracting telescope, meaning it has a lens at the top, in the world. It was installed in 1897. And what is very important when we think about the dimensions of a telescope is not so much the length, but the width, because the width determines how much light comes in. That's basically what a telescope is. Think of a telescope as a bucket that collects light. Your eye collects light, but it's only got the pupil is the opening, and it's only a few millimeters wide. A telescope, which needs to look at things very, very far away, that we get very little light from those things, sometimes traveling over millions of light years, needs to collect as much light as it can. And so we need a very wide opening. So we refer to this as the aperture. A refracting telescope needs to be very long with a large, heavy lens. And this is the downside of a refracting telescope. It needs to be wide to collect a lot of light, but it's very top heavy because you have a very heavy lens at the top. And the larger you make the telescope, or the wider you make the telescope, the heavier that lens needs to be. And so it's very top heavy, it's unstable. Also, another disadvantage of having a lens up there is that glass tends to reflect some light. You look in a window and you see, hopefully the main thing you see is what's beyond the window, but you can also see your reflection. You see things behind you reflecting in that glass. And so this glass lens reflects some of the light away where we really want all the light to come into the telescope. But this is one model, and it's called the refracting telescope. And then there are reflecting telescopes. The idea behind reflecting telescopes is that they have a curved mirror on the bottom. Now, these are three separate designs of reflecting telescopes. You don't have to, for this class, know the differences between them, but I'm just showing you these different designs. By the way, Isaac Newton is the one who invented the reflecting telescope in the late 1600s. Let's look at this design at the in the middle of the page. Starlight comes in. Notice there's no lens at the top. The starlight comes in. It gets to the bottom of the telescope, and there is a reflecting mirror. It's called the primary mirror. And then it starts to converge. So those light rays come together to a focus. Before they actually come to a focus, they are bounced out the side of the telescope by this secondary mirror. So they haven't yet come to a focus, and then they finally do right here, and we put an eyepiece, which has a lens in it, and that actually helps to gather the light appropriately so that we can look into it and see the image. And you can see on the left and right these other designs, but this middle one, what I've described, is the basic idea of a reflecting telescope. Reflecting telescopes are what are used in observatories. Professional observatories use reflecting telescopes because the bigger it is, the wider the aperture, then we can gather more light. And when we're looking at deep sky objects, things that are maybe millions of light years away, we need all the light from it we can get. So we need it to be wide, and a refractor with a lens at the top, as I described before, can only be so wide before it becomes impractical. Well, here are some very large telescopes. We have the twin Keck telescopes on Mauna Kea Mountain in Hawaii. And when you look inside, you can see there's the reflector right there. You look inside, and there is a person dressed in orange sitting in the middle. You can see a size comparison. So these reflectors are about 10 meters in diameter. And in fact, you don't even have to have one smooth curved surface. Very often when we have telescopes this large, it's divided into many hexagonal segments. So depending on the size of your screen you're looking at, you can see it's kind of like a soccer ball. A soccer ball is divided into hexagons and pentagons, but this thing has many hexagonal segments about 1 meter across. And they all together act like a curved mirror. Imaging with telescopes. Astronomical detectors can detect forms of light that our eyes cannot see. So you think across the electromagnetic spectrum, and visible light that our eyes can see is such a small part of the electromagnetic spectrum. And while it was very good, it opened up astronomy in the 17th and 18th century with visible light astronomy. We learned so much. We were able to see so much more when we eventually got into being able to use infrared telescopes and X-ray telescopes and telescopes that cover the whole range of the electromagnetic spectrum. So we see in this picture that looks like the remnants of a supernova, we see this is from an X-ray telescope. And there is false color that's introduced because you think if this is X-ray, it's not going to actually look orange or blue or yellow, because orange, blue, and yellow are visible light waves that our eyes can see. But what's happening here is there is X-ray of various wavelengths, and then a computer is used to add false color so that our eyes can see and appreciate different things that are going on. So, for example, the computer programmer chose to make the highest energy X-rays blue, the medium energy X-rays green, and the lowest energy X-rays red, so that we can look at this and we can see, kind of along with the electromagnetic spectrum, red is low frequency, blue is high frequency. We can look at this and immediately see, okay, it's all X-ray, but this is lower frequency. The green is medium, the blue is high frequency. So be aware that often when you see pictures, they are, in astronomy, they are false color. This is a picture, it's a composite picture taken with radio telescope and visible light telescope. This is of something called a radio galaxy. Now, if you just looked at this picture through a telescope with your eyes, looking with visible light, all you would see is this bit in the center. That's the visible portion. What you would not see is the larger parts of this galaxy, these lobes that extend from it hundreds of thousands of light years in both directions, and these are called radio lobes. So they are at least in terms of size, the most dominant features of this galaxy. And if we only looked with visible light, we would miss those features. This is a side-by-side picture of the Dumbbell Nebula, otherwise known as M27. On the right is the kind of picture you see on the internet or in textbooks, and on the left is what your eyes would see. Now, the reason for the difference, and this is typical of doing astronomy, we get these beautiful pictures on the internet and in textbooks. We look with our eyes and it looks like a gray smudge or a gray blur. The reason is that when you look at something with your eyes, such as the picture on the left, your eyes gather light for about 1/10 of a second. It's like a filming of a movie. A movie is actually many, many frames all stacked together, and it looks like a moving picture. And that's what your eyes do. You gather light for about 1/10 of a second, and then that image is essentially deleted, and then your eyes gather light for the next image that's about 1/10 of a second and send that to the brain. So you only get images that are about 1/10 of a second long with your eyes. And when you're looking at something millions of light years away, there's only so much light you can gather in 1/10 of a second. But a picture like this on the right is taken with many, many exposures that sometimes last many minutes, and sometimes it's hours long of exposures stacked on top of each other. So the picture on the right is what you get when you gather light from a source such as this nebula, but it's many, many, maybe hours of light, and all the color and all the detail starts to come out. Do you want to buy your own telescope? Well, here is some quick consumer advice. First, I suggest if you want to get into astronomy and you don't know how to get started, but you think you want a telescope, I suggest buying binoculars first. Now, binoculars tend to get marketed based on their magnification and the width or the diameter of their objective lens. And so, for example, 7x50, that's a good starter binoculars. 7 means the magnification power, and then 50 millimeters. You can get much more for the same amount of money. You won't spend that much money on a decent pair of binoculars. Another thing for buying telescopes is ignore magnification. If a telescope says on the box that this telescope is 200 power, 200 magnification, ignore that. It's a sales gimmick. While that is a useful number for binoculars, such as the 7 power binoculars, with a telescope, it's not as important. With a telescope, there are other things you can do to increase, or sometimes you want to decrease magnification. When you're looking in details, maybe at the moon, often you want a decreased magnification. Sometimes you want to increase magnification. But you to change that magnification, you can just change out different eyepieces. So the magnification isn't really a factor of the telescope itself. Things you should be looking for are the aperture size. Typically, like with this number 50 on binoculars, that's 50 millimeters, the diameter of the lens, that's what you're looking for. So it's typically measured in inches or maybe millimeters. The telescopes at the college are 10-inch telescopes. That means it's 10 inches in diameter. And in general, the larger the size, the better off you are. You can gather more light that way. However, there are disadvantages to large size because depending on how mobile you want to be with the telescope, the setting up, the maybe carrying around, maybe it's someplace or some telescope you want to take away on vacation while traveling. The disadvantage to a large telescope is it's more cumbersome, so that's what you want to think about. But in general, for viewing purposes, the larger the better. Optical quality. So just like almost anything in life, there are good quality companies, companies that make good quality products and inferior quality products. So you want to read reviews on these different products. And as I mentioned before, portability. Think about where you want to be taking this thing. I recommend doing consumer research. Look at magazines such as Astronomy, Sky and Telescope, Mercury, visit local astronomy clubs, go onto websites. Astronomers, even amateur astronomers, will have often much advice and opinions of what makes a good first telescope. Things to avoid. This is just an advertisement I pulled off the internet when their big thing is an image like this. This is an image that is supposed to wow us, but it has nothing to do with the quality of the telescope. And if they're putting something flashy like this with the astronaut floating in space and these terrain features on the foreign planet, these are things you will never see with your telescope, at least the richness of those terrain features, then they are trying to show you something flashy instead of actually focusing on the quality of their product. Avoid a flimsy tripod or mount. And this goes to just reading reviews of products on the internet. This to me, I can just visually see this is a flimsy tripod, and what backs it up was on this particular product, I think it had like a $70 price tag, which is much less than you should expect to pay for a quality telescope. But if the tripod is flimsy or it's unstable, you will be so discouraged. You won't be able to see anything good. The tripod is very important that it's very stable. Let's look at telescopes and the atmosphere. The atmosphere has great effects on our viewing things in space. Our goals for learning: how does Earth's atmosphere affect ground-based observations, and why do we put telescopes into space? We have atmospheric distortion. We've got 60 miles of atmosphere above us, and the atmosphere causes distortion of our viewing of the light as the light goes from outer space down to us. The best ground-based sites for astronomical observing are calm air, so not too windy, high altitude, so the higher up you go, such as on mountaintops, the less atmosphere you have to cut through, dark, so far away from city lights, and dry weather, which means places that have few cloudy nights. Atmospheric distortion is the reason that stars appear to twinkle. Look at this picture here. You have a star, and the light travels pretty much unimpeded through space because there isn't much gas out there in space. Very, very empty. But then it hits the atmosphere. And the atmosphere distorts the light, and it distorts different wavelengths in different ways at different times. So at any given split second, blue is doing one thing, green is doing one thing, red is doing one thing, orange, and you can see it all bouncing around. And all this is happening in the wink of an eye, split seconds, where you have all these different wavelengths coming to your eyes in different at different times, at different angles. The result of this is that you see the star twinkling because the light is doing these chaotic things. Now, when a particularly bright star is low on the horizon, you will actually sometimes see a star seem to go between red, white, and blue, or green and orange. It'll seem to actually be changing color. The star itself isn't changing color. It's just that, as this picture shows, different wavelengths are hitting your eyes at different times and from different angles. I mentioned a minute ago when a star is low on the horizon. You can think when a star is straight overhead, that's when you're going to get the least distortion because there is less atmosphere for that light to travel through. So you're going to get less twinkling. However, when a star is more on the horizon, it travels through much more air and there's therefore much more distortion and weird things can happen. This is the same reason that a sunset looks red or orange, or the moon low on the horizon has more of an orange or yellow look to it as opposed to a white look when it's high up in the sky because of what the atmosphere does. Well, all of this is very bad for astronomy because if we want to look out in space and see the things that are out there, we want as little distortion as possible. So the best viewing is actually when we are looking straight up overhead, so there's less distortion, and hopefully, of course, we don't want any clouds in the sky, and we want less turbulence in the air. The best observing sites are atop remote mountains, calm air, high elevation, dark skies, and dry, non-humid weather. So this is the summit of Mauna Kea in Hawaii with the Keck telescopes. We put telescopes into space, such as this one that is in orbit around the Earth. Not only does our atmosphere distort light, but with many wavelengths, it actually blocks the light entirely. So we need to put telescopes up in space. Now, these are not space stations that people go up to and observe because of computers and modern communication. What we have is these telescopes, these observatories up in space. They look at whatever they're looking at. It could be galaxies, black holes, neutron stars, whatever. They gather that light and then they send the images, they send the information down to Earth where it's analyzed. You can see up at the top major space observatories, but let's look here at the atmosphere. What you see is the electromagnetic spectrum. So remember the order from high frequency to low: gamma, X-ray, ultraviolet, visible, infrared, and radio. And buried here between infrared and radio is microwaves. You see with gamma rays, the gamma rays, remember, are ionizing radiation. They are harmful to biological tissue. They're harmful to our bodies. So are X-rays, so are ultraviolet rays. One of the many blessings that we have is in our atmosphere. Not only that it provides us with oxygen to breathe, not only that it locks in heat to give us stable temperatures, but it guards us from all of these wavelengths, these harmful wavelengths that are out in space. Now, this is good for life to exist, but it's bad for astronomy. So if you have a gamma or an X-ray telescope or ultraviolet on the surface of the planet, those rays are not going to come down to us in large enough amounts that we can do any imaging. So we send telescopes up higher. So we have here an image of a weather balloon, 10 kilometers, that's about 6 miles high. 100 kilometers, that's going to be 60 miles high, 62 miles. And that's where we say generally is about the extent of our atmosphere as it gradually thins out. So we need to have gamma ray observatories way up high. And X-ray observatories, we have to have those up high to be able to do this proper imaging. Then the light, as we go to lower and lower frequency, lower energy, it breaks through our atmosphere. So this is another, I think, miraculous thing about our atmosphere. All of the harmful stuff is blocked. And then you get to ultraviolet, which is just shy of visible light, just a little higher frequency. and then you get into visible, and then it all comes through. And this is very extraordinary because visible light is lower energy than all those other wavelengths, than gamma, X-ray, and ultraviolet. So you would think that it would have more trouble penetrating our atmosphere, but yet it comes down through. Now, an amazing thing for astronomy about this is that if visible light did not come through our atmosphere, if it was blocked, just like gamma ray, X-ray, and ultraviolet, then over the millennia, people would have never seen anything that's up there. People would have never wondered what's up there. They might not have ever wondered, is there anything up there? Because there was never any sense of anything being up there. Stars, planets, the moon, they would have never seen it. But we have been able to enjoy through the millennia, even before telescopes were invented, we've been able to see and enjoy creation that's out there and wonder about it and speculate. And now we've developed technology that helps us to look at it even more. So visible light comes through down to the surface, of course not when clouds are blocking the way, but generally through the atmosphere, visible light comes through. So we can do astronomy on the ground. And then as soon as you leave the visible spectrum, you get into infrared, the atmosphere starts blocking it again. That's very interesting that the thin sliver of light that our eyes react to is that same thin sliver that actually comes through the atmosphere. So as you go into lower wavelengths, you have to have your observatory higher and higher up. So we have infrared observatories on mountaintops, but you get into lower frequencies, and even on mountaintops, there's too much atmosphere blocking, but we have infrared observatories in airplanes. And then radio waves. This is another part, the weakest part of the electromagnetic spectrum. It comes through the atmosphere just fine. So we can have radio observatories down on the ground. So one thing I want you to get from this slide here is what I've written at the bottom. Only radio and visible light pass easily through Earth's atmosphere. All other parts of the electromagnetic spectrum, we have to put observatories or telescopes higher up. How do we observe invisible light, which is everything except visible? A standard satellite dish is essentially a telescope for observing radio waves. If you think about earlier in this video, I showed you a reflecting telescope, and this is pretty much the same design. You have your curved surface, and it reflects the rays into this. This kind of acts like the secondary mirror for the reflecting telescope, but it reflects the signal there, and then those signals are electronically processed and gives you your TV show, whatever you're watching. A radio telescope is like a giant mirror that reflects radio waves to a focus. This is the Arecibo radio dish in Puerto Rico. It is very large. It's about 300 meters in diameter. That's about 3 football fields. But look at the reflecting design here. You have your curved mirror surface, and then it reflects the signals up here, and then those signals are processed electronically by a computer. Now you might be wondering, why such a large telescope? One of the laws of physics and optics is if you want to do imaging, with whether it's a mirror or a lens, but if you want to do imaging of something, the diameter of your surface, such as what you see here, needs to be at least as large as the wavelengths that you're imaging. So whatever the wavelengths are, it has to be bigger. Now with visible light, that's not an issue, because with visible light, we're talking about hundreds of nanometers, hundreds of billionths of a meter. And we have telescopes that are centimeters or inches across, sometimes meters across. So this isn't really an issue. It's only an issue with radio waves. And with radio waves, you can have wavelengths that are 100 meters, even 1,000 meters, maybe even 10,000 meters across. If you're going to do imaging with those wavelengths, you need a telescope that's at least that big. So the Arecibo radio dish is meant to examine radio waves with long wavelengths, even as much as a few hundred meters. Unfortunately, in 2020, a main part of it fell and did a lot of destruction to the dish. And so this is the state that it's been in recently. Infrared and ultraviolet telescopes. On the left is an airplane-based infrared telescope called SOFIA. And on the right is the Spitzer telescope. This is a painting of it, the Spitzer telescope. Infrared and UV light telescopes operate like visible light telescopes, but they need to be above the atmosphere, or at least with the airplane, it has to be above much of the atmosphere to see all the wavelengths. An airplane that's about 37,000 feet up is actually above about 3/4 of the atmosphere. Now, distance-wise, 37,000 feet is not 3/4 of the way up. You have many, many more miles to go. But because the atmosphere is thicker down here near sea level and it gets thinner as you go up, if you get up to about 37,000 feet, where an airplane like this can go, you have cut past about 3/4 of the air. This is the big thing in astronomy observation these days, the James Webb Space Telescope. I think it was originally set to launch in 2016, but there were many delays. But finally, it launched in 2022, and its purpose was essentially to replace the Hubble telescope. This is a painting of it. You can see the reflector telescope design. There is the with the hexagonal plates. There's the surface that the rays bounce off of. They converge, and this is what collects the rays. The primary mirror is 6.5 meters across. It is made of 18 gold-plated hexagonal segments, and it looks at wavelengths in visible and infrared. It orbits the sun, but it sticks close to the Earth. So these, what you see in this image, these are called Lagrange points that basically have to do with the physics of orbiting bodies. The L1 point, the L2, L3, we don't get into that in this class, but the L2 point is just a good point between the sun and the Earth. Actually, it's on the opposite side of the Earth. And it points outward, and as the Earth goes around the sun, it follows the Earth, or it goes alongside the Earth. So it's actually orbiting the sun, but it sticks very close to the Earth. And we call that the second Lagrange point. The Hubble telescope, which went into operation in the early 90s, gave us astounding views of things up in space. But the Webb Space Telescope is already giving far superior images. Here's the side-by-side comparison of a planetary nebula. On the left is the Hubble image, and on the right, the Webb telescope image. You can see the white dwarf right in the center at the dividing line, but you look at the detail, the resolution that Webb gives that's far superior to the Hubble telescope. Here's another side-by-side Hubble's image of the pillars of creation on the left, and on the right is the Webb Space Telescope image. This is a cluster of galaxies, Stephan's quintet, and you can see the different resolution. Hubble on the left, Webb on the right. And here is looking into the farthest reaches across the universe. Hubble on the left, and we get much brighter detail, resolution, and color on the right from Webb. This is a painting of the Chandra X-ray Observatory. X-ray telescopes also need to be above the atmosphere. If we want to look particularly at very high temperature things, such as the hot bubbles that come from supernova explosions, also from the accretion disks around black holes and neutron stars, we need X-ray telescopes. You can see in this schematic here, the X-rays come in, the first set of nested mirrors deflects X-rays to the second set, and the second set of mirrors deflects the X-rays a second time to the focus point. Focusing of the X-rays requires special mirrors. The mirrors are arranged to focus X-ray photons through grazing bounces off the surface. And then as this information is gathered, it is sent to computers down below where it's analyzed by astronomers. This is the Fermi Gamma Ray Observatory. Gamma ray telescopes also need to be in space. Focusing gamma rays is extremely difficult, and so it's a big feat in astronomy that we're able to have gamma ray telescopes. Here are a set of radio dishes. How can multiple telescopes work together? Remember before when I showed the Arecibo radio dish, I said that the telescope needs to be at least as large as the wavelengths that you're imaging. But what if you want to image wavelengths that are a kilometer long? Well, you don't necessarily need one big radio telescope that is a kilometer wide. We use a technique called interferometry. It's used for linking two or more telescopes so that they have the angular resolution of a single large one. So when you have these radio dishes, they all point in the same direction, and together they gather the information, they gather the radio waves, and they act like one big radio dish. So interferometry allows these two small radio telescopes to work together to obtain the angular resolution that would be achieved by a single much larger telescope. And there you see the picture that I started with in this video, and so I'll conclude with the same picture. All of these radio dishes work together to get images of whatever target they're looking at, and all those signals are combined to act like a very large radio dish. And that is the end of Chapter 6, Telescopes, Portals of Discovery. Have a great day.